Okay, perfect. Um, yeah, a really quick introduction about myself. I'm part of the WARR Space Elevator Team. The team has been there since 2005. As you then already mentioned, the WARR already does also does other projects such as rocketry related projects, robotics, satellites, you name it, we probably do it. I personally joined the WARR in 2020 when I started my bachelor's degree. I've been team lead of the space elevator team since about 2023. And I myself have a mechanical and aerospace engineering background with a focus specifically on embedded systems and control theory and things like that. So I think today I will more focus on that side, so on the electronics and software side, and there will be a talk later on with a more detailed mechanical sizing concerns. Right, so really quickly to go over our agenda, I would like to do this with the example of the WAL Space Elevator's climber, which is called the Gaxa. I will get into the naming really soon. Quickly go over the mechanical system and then talk about our electronics and our software and kind of how things are looking there and what kind of things somebody needs to consider when building a climber or when designing a climber, and then I will just quickly go over what's next for us at the Gaxa team. So yeah, this is the Gaxa on the right. Gaxa is basically a Bavarian word for a mountain climber. And so yeah, there's that's the whole naming idea behind it. There's no fancy acronyms or anything. It's just a climber in Bavarian. Since we are a Bavarian team, that was the thought process behind it. Here's some pictures to give you just a quick idea of what this thing looks like. Now I'm quite short. You can see me. Where's the laser pointer? There we go. You can see me here. I'm quite short. However, the climber is still pretty tall. I would say about 1.5 meters more or less. You can see a little bit of the internal components here. I will go over later on. And this here is the climber with its side covers on at the Japanese competition where we'll be participating again this year. Right, so what do you have to do to design a climber? As Julian's already alluded to, one important part is systems engineering. So this is kind of where we go from having, a certain problem or having a certain idea, and we go to a finished design. It's a bit of an iterative process if you do this, if you really go into this deeply. And basically the first step would be to, have a set of requirements, what you have to do basically to say, for example, based on some certain competition rules or what you want to do exactly with the climber, or maybe even personal preference. I know that's played some role for us, for example, or obviously some safety concerns. So you would have create a set of requirements, a set of basically rules that you have to follow, what the climber needs to do for it to fulfill its role. Yeah, and then based on these requirements, you can build a concept. You can then implement that concept, and obviously, at any of these steps, you might notice some things that are not going well or that are not going to plan or things that were not considered. And then you would basically go back and implement those as well. And then, kind of, this is where the iterative process comes in. Yeah, once you're done with all of that, obviously, we need to somehow prove that these requirements were fulfilled, and that's where testing comes in. So obviously, testing is also a big part of developing a climber. Um, some of it is done at competitions, but obviously, ideally, you would do some testing before the competition to really know that everything's working once you get there. All right, as I've already promised, I will keep my mechanical introduction short. I will just quickly go over our thought process behind the Gaxula 4, what we've done on the mechanical side, and I will not go too much into sizing and different concerns there. Obviously, since our goal at the end of the day for a real space elevator would be to carry as much payload as possible into orbit, the structure has to be as light as possible. This is the same idea with rockets. For this reason, we've gone for a truss design where we use carbon tubes basically, and then we have structure plates tying the whole thing together. Additionally, you can use these structure plates to attach different things such as the wheels and the wheel shafts. and counter wheels and the motor and everything like this. You can connect to these structure plates made out of aluminum. You can see some here being manufactured at the makerspace, which Julian has mentioned. This workshop, this shared workspace where we get access to. Yeah, exactly. And the idea is basically we went for this truss design because it's quite easy to calculate. There's no topology optimization of certain parts or stuff like this. The math behind it is quite simple, and obviously carbon fiber is very good when it comes to tensile loads. Yes, that being said, the next kind of thing you have to look at is the drivetrain. And this is sort of where it ties into the electrical systems. So there's different things to consider for a drivetrain. Obviously, you need brakes to stop the climber. Say if you have an emergency, if something's going wrong, if you have a motor problem, stuff like this, you want to be able to brake so the thing doesn't fall into the ground. Um, Obviously, we need a motor um, to move the entire climber. Here, one thing one needs to consider is if you want to use a direct drive system, so you have the motor directly driving the wheels, or if you want to go for a geared system, so you have a motor driving a gearbox, as you might be familiar if you've done any mechanical engineering. Personally, us in the 4.3, we use the gearbox, so we have a planetary gearbox on the other side that translates the motor with a 1 to 10 gear ratio onto the wheels. And then we have belts driving basically the outer two wheels where the brakes are sitting on. Yeah, and basically this is where we come into the electrical side. This is where I would like to go into a little bit more detail because it is sort of what I'm very familiar with, as well as that we were quite advanced here. So looking at our entire electrical system, we have two sort of electrical buses. We have a low power bus and a high power bus tied to the main battery. The entire goal of the main battery is to drive a motor driver, which then obviously drives our motor. We have an emergency stop here, so if you press the big red button, the climber stops immediately, just in case somebody gets caught on the tether or something like this. Yeah, and all the control electronics are driven off our auxiliary battery. We have a power distribution system which translates this 12 volt input from our battery, which obviously reduces as the state of charge reduces, into stable voltages we need to drive our brakes and the traction control, which are lower in voltage than the main motor driver, as well as all the control electronics, which typically take between 5 and 12 volts. Yeah, and basically then we have control electronics. These control electronics are responsible for kind of doing everything related to the climber control. So they're supposed to monitor the entire climber, make sure everything's going well, kind of track where the climber is on the tether, how far it needs to go, what sort of signals we need to drive the motor with, and stuff like this, as well as obviously controlling the brakes. Looking closer at our control electronics, this is sort of the structure we went with. So we have three boards, of which two are basically the exact same board. Um, the PTBs, the peripheral transceiver boards, are responsible for collecting sensor data and sending this to the control unit. And the control unit, on the other hand, then takes the sensor data, calculates the certain signals that need to be sent to the motor, to the brakes, to the ground control station, stuff like this, and sends these out. Our entire climber is sitting on a CAN bus. So if we ever want to add any other system and stuff like this, we can just put it in the CAN bus. Sort of similar to what cars use, and as well as the motor, which also sits on a CAN bus. And this gets interesting if you want to add more motors. Say if we want to, for example, add motors on the outer wheels as well, this is something where CAN bus would really shine because we don't have to kind of add extra control interfaces to our control electronics, but we can just extend this CAN bus to the other motors as well. Right, so as I've already alluded to, there's different sort of responsibilities that we have for the control electronics. Obviously, the control is a really important one. We need the sensor data for this, which I will get into later. Um, the control is responsible for determining where the climber is and how it should control the motor to get it where it should be. So say, for example, if we're starting at 0 meters, the climber wants to go to 100 meters. It needs to know obviously where it is at any point in time, as well as obviously when it should stop. So in our case, say if we have a competition going straight up for 100 meters, we want to stop at the top, so at 100 meters. Obviously, if we need to, we should engage brakes. Yeah. Then we have sort of control communication with our ground control station. We have a ground control station. The idea behind it is to sort of safely be able to operate the climber from further away. This works through an antenna uplink, which is used by the control electronics to communicate with the ground station. And this allows us to sort of monitor what the climber is doing, get sensor data, as well as send certain commands, tell it to stop now, tell it to stop at 20 meters, tell it to stop at 40 meters, stuff like this. So we have total control over the climber at any time, even if it is, let's say, out of physical reach. Yeah, and then sensors, obviously really important. We somehow need to know where the climber is. For this, we have these two extra boards, which will collect sensor data, send this sensor data via CAN. Here, obviously, there's thoughts of what different sensors we want to use. So what sort of sensors give you useful values, and how can you get these sensors to give you good measurements? Now going just really quickly, because I don't want to bore you too much, over the control electronics. I have one of these boards with me. It's quite small. It is quite a powerful board. It's based on a RT1060, which is just a microcontroller. It doesn't matter too much. Yeah, it should estimate the climber position based on the sensor data, and it then uses this to drive the motors through a series of PID controllers. If you're familiar with control theory, you might know what I'm talking about. Otherwise, it's basically just multiplying you calculate an error based on where you want to be and where you are, and then you multiply this with some gains and you receive a certain output command. Yes, the control board is also responsible for sort of monitoring the entire climber, monitoring every other subsystem, and making sure that every system works as it should and does what it should and is alive and is communicating. And if this is not the case, it will then go into certain fail-safe modes. This is again to, make sure that if we lose, for example, sensor data, that we act in a certain way, or if we lose the ground control link, that we act in a certain way. Really just to make sure that, we're really safe at all times and nothing can happen due to some bad connection or something like this. Additionally, something we have realized is quite important is something we have realized, which is quite important, is data storage. So we have an SD card on here, which will just log all the sensor data and all the control inputs and stuff like this. So this will really help us sort of evaluating what went wrong if something went wrong, or evaluating what we can do better if everything went well. Yes, additionally, something I would like to do later on is introduce you to some boards we've designed for the WSPEC. I think, Morty, if you could remind me just really quickly, once we get to the questions, I will quickly get over this because I will have to exit the presentation. But we have some boards we have designed to maybe make your life easier a little bit for the next few competitions. But again, I will get into this really once I've gone through the presentation. Yeah, just quickly scrolling through further here. The next kind of thing we have are the sensor boards. Here really the main idea, the main question you have to ask yourself is, what sensor data do I want to have? So in our case, we sort of always went with a Lidar already. A Lidar is basically a sensor which tells you how far a certain point you're pointing it at is from you. So sort of like a rangefinder. Maybe you've seen those small ultrasonic devices that you can buy for Arduinos for really cheap on Amazon and stuff like this. They're really similar idea, just with light instead of sound waves. Um, Additionally, a sort of more advanced idea we've went with is the inclusion of an IMU, so an inertial measurement unit. This allows us to keep track of our acceleration um, in three dimensions, as well as our rotation in three dimensions. And by continuously integrating this acceleration, we can basically get the position the climber has moved, or basically the distance a climber has moved. So this can be used as well to sort of estimate our position, um, and kind of really know where we are on the tether. Yeah, again, really quickly, as I've alluded to, we have a power board. Its job is just to take a battery input. There's a big connector here. You plug in a battery. Oh, sorry. You plug in a battery here, and then you have your outputs here, which are monitored. There's a few sort of protection circuits to make sure we can't really burn through anything, to make sure we don't damage the battery and stuff like this. We have protection circuits which will shut off the power supply if we're about to damage the battery in any way. Yeah, in the future, what we plan to do is add a microcontroller on here, which will be able to individually sort of switch every in and output. So we can sort of control which systems get power, as well as monitor how much each system draws in power. This is really helpful for us to sort of determine, what systems really take a lot of power, which systems maybe we should shut down when we don't need them, and stuff like this. Yeah, really important parts, as I mentioned, the big red button is the human interface. This will basically sit on the climber, and this will allow us, to make any last minute changes or anything like this through display. Start the climber with this tiny green button, as well as, in any case, stop the climber through the emergency stop button, as well as the thing you can see here. There's a pin normally inserted in here, and as long as the pin is inserted, the motors do not get power. So this is just an extra safety measure we have, so we can make sure that when we stand next to the climber, nothing can happen to us because the motors do not even have the power to run. Yeah, additionally, we have a small microcontroller here, just because we can, to control the display. Um, this is really a low-powered MCU. It doesn't really have any important jobs. It's just here to, show us what state the climber is in for a few LEDs and kind of collect these inputs we make and send this further to the control board. Yeah, so we've had a lot of electronics now. Now the question is writing software for it. We've went with quite a fledged out system, um, which you can see here. So again, we have the different electrical components, and within each of these boards, there's different software modules that have different responsibilities. So for the sensor boards, obviously we have the collection of data through Lidar, GPS, which I haven't mentioned, or GNSS, the inertial measurement unit, and we have cameras also recording. And we send this through CAN bus, and then we have the main control board, which sort of has this monitoring feature, this kind of supervisor which tells every module which state it should be in, and the drive controller, which is sort of the really important part. We have our ESCs, and we have the downlink to the ground control station. So this is the way we communicate with the climber while it's driving. This is the way we can, give it commands at any point. Yes, and yeah, for the software, for the for the control board, because this is the big one. The sensor boards are quite simple. At the end of the day, they just read some sensor data and send it to the main control board. This is really the more complex one. So we have again this watchdog module, which will sort of supervise every module and tell us which state it's in, tell us if it's healthy, tell us if it's doing good. We have the interfaces to the other subsystems, or to the other electrical systems, and then we have the drive controller. And the drive controller is basically where all the all the interesting control stuff happens. Um, so basically, we have a our structure. In our structure, we have a Kalman filter. Basically, this is a sort of estimation of your state based on some sensor data. You can basically propagate your state through time and then take some sensor data and sort of correct your estimation through sensor data. So this is the way we estimate our position and speed. We get the sensor data, obviously, from the sensor boards. We estimate our position and our speed, and then these are used as inputs for our PID controllers. First in the position, and then as a sort of cascading design, the position command or the desired position is subtracted from the actual, or sorry, the speed command, which comes out of the position controller, is subtracted from our actual velocity, and we receive an error in our speed, and this is then controlled by a second controller, which then sends out our motor commands, or which then gives us our motor commands. All right, quickly going over what's next for us. Segaxler 5.0. You can see mechanically a lot will change here. The electronics and the software will sort of stay the same, which is quite nice because we try to make it modular in a way where we don't have to, for every iteration, change everything, but we can just change certain things without having to, completely scrap everything. We will have 4 wheels on the new design. Each wheel will have its own motor, which you can see here. These are the TQ motors that we got sponsored. This is sort of split into 2 climber halves. So you have the top and the bottom half, which can move relatively to each other through linear actuators. And this will allow us to... Oh, sorry. Not used to talking so much. This will really help us sort of dynamically control the traction, so that in the beginning, when we're stationary, we need a lot of friction on the wheels, so we can move the climbers closer together or press them closer to the tether. And as we move faster, we don't need that much traction, so we can sort of reduce the traction through these linear actuators. Yeah, the other good thing about this, or the other advantage about these linear actuators, is that it's significantly easier to install on the tether. I'll quickly jump back to the I didn't think of this. So this is our old design. You can see here there's these sort of towers with counter wheels, which create a traction force on the tether. And these have to be installed by manually screwing in 4 screws, or 6 screws, I guess, for each wheel. And this is quite time consuming. I think last year in Japan it cost us about 10 minutes or more. So obviously this is not really sustainable. So the idea here is that if we have 2 climber halves and we have these linear actuators, we can use these to sort of move the 2 climber halves apart, put it on the tether, and then move them together and kind of fix the climber on the tether. This would really reduce the time we need to install um, the climber on the tether for competitions, which obviously is a big time sink, or at least it was a big time sink for us. If you have short competition slots, it's sort of really important to not use every minute you can to actually drive with the climber and not install it on the tether. This is just maybe a thought for you if you start designing a climber for competitions. This is something we have learned that is really important to consider, because again, it takes a lot of time. Right, then quickly before we get into questions, I would just show what I wanted to get into earlier. If you give me one moment. I obviously didn't prepare this in my infinite wisdom. So the idea is basically we're aware that especially now starting, if there's a competition in a year, there's a lot of things to do. There's a lot of mechanical design to do. There's a lot of software design to do, and a lot of electrical stuff. There's a high possibility that not all of these will be possible within the allotted time frame. So at the WSPEC, our idea was to basically create some electronics, which we would be able to offer to the teams. So if they don't want to go through the effort of designing their own PCB or maybe, having any concerns about that, we could offer a PCB basically with just as many, with a microcontroller on it, obviously, and as many connections as possible. So, you're open or you're free yourself to decide really what kind of sensors and stuff like this you want to use. But you don't really have to put any thought into, PCB design and selecting a microcontroller and stuff like this. And additionally, the idea was to create this as a sort of stack. So you can add certain PCBs, which would then interface with the main board through these connectors, and you could use this to sort of forego the electrical design stage and instead really focus on, maybe the mechanical and the software design for the first iteration, and then you can, do your own electronics in the future. Yes, this is just something I wanted to mention since we have this option. So here, for example, you would have a servo expansion. You could connect this with a GPIO port on here, and this would then allow you to drive three different servos through these connectors here, without having to, put really any solder effort into this. Just because we're aware that this is quite a challenging topic. Yeah, but that's it for me. If there's any open questions, I'm obviously really happy to answer any. And otherwise, I think I would continue with the next talk.